Okay, let's talk about Descartes. That's how that's pronounced, Descartes. His rule of signs. This is kind of complicated. And honestly, I don't find it that useful. But here it is. We're going to learn it. This is a quick way to check how many positive or negative roots or zeros a polynomial could have. So we do two different things. We leave the function alone and we see how many sign changes there are. How many times the signs change from positive to negative or vice versa. We count those. That will give us a clue on how many positive solutions we have, how many positive roots. Then we replace all of our x's with a negative x. We count again how many sign changes we have, and that will tell us something about how many negative real zeros we have. So, for example, this guy has only one sign change. Look, we're positive, stayed the same, still positive, still positive, still positive. Oh, we switched to a negative. That's one change. Then when we replace all the x's with negative x, remember an even number of negatives will stay the same. An odd number of negatives will get the opposite of what we had. Negative 1 cubed is negative 1. Negative 1 squared is positive 1. So then we would count how many sign changes we have here. So I switched from positive to negative. That's one change. I switched again back to positive. That's two changes total. Another switch, three changes. And then we stayed the same. There's no change there. So after replacing x with negative x, we had three sign changes. That will tell me something about how many negative zeros I have. Okay, so I keep saying something about. Here are the rules that you got to learn. When you leave the function alone and you count the sign changes, the number of sign changes equals the number of positive roots minus possibly an even integer. That sounds weird. So let's say I go through and I have 8 sign changes. Then the number of possible positive roots will be 8 or 6 or 4 or 2 or 0. I keep subtracting 2. Say I count the number of sign changes and I get 3. Then the number of positive roots will be 3 or 1. I keep subtracting 2 until I can't subtract 2 anymore. Similarly, once you've replaced all the x's with negative x's, however many sign changes you get, you might have that many negative, because we've done the negatives, you might have that many negative zeros, or you subtract 2 from that, until you can't subtract 2 anymore. Okay, here's an example. So here's my original. So we're going to go through and count our sign changes. So going from negative to negative, that didn't change. Negative to positive, we're always going from left to right. There's one change. I change from negative to positive. And then I change again. And then we stayed the same, still negative. There were 2 changes. So the number of positive roots is either that number of changes or that number of changes minus 2. And I keep subtracting 2 until I can't anymore. So we either have 2 or 0 positive real roots. And it doesn't tell me which. We're guaranteed we either have 2 positive roots or none at all. And we don't know which one. But I guarantee you, here's the key. If we find one positive root, we know there has to be another one, because one is not a possibility. Okay, now we replace all the x's with negative x. So we got to be really careful with our pluses and minuses here. So I'm calculating f of negative x. Negative x to the 4th would be positive x to the 4th. That extra negative that was already in the guy comes along for the ride. Negative x cubed would be negative x cubed. A negative cubed keeps the negative. But I already had a negative here, so a negative times a negative will be a positive. I've got a plus here, so that comes along for the ride. Negative x squared. Even powers kill negatives, odd powers keep negatives. Negative x squared is just x squared. So notice we're positive here. Negative 4 times negative x will be positive 4x and then minus 12. Now we go through and we count how many sign changes there are. So I switch from negative to positive. That's one sign change. Stayed positive, no change in this region. Now I'm changing from positive to negative. So there are two sign changes. That means that this original function either has 2 or 0 negative roots. So we know we got 4 roots altogether. We know that. We're guaranteed we have 4 roots. It's a 4th degree polynomial, 4 complex roots. There's no guarantee we have any positive or negative roots at all. So here is the breakdown of everything possible. And here is the actual graph. We do have 2 real roots. We only had 2 real roots. Notice they're both negative. Okay, let's do an example. Decartes' rule of signs always takes a lot of practice. So f of x is 2x to the 4th minus 10x cubed plus 11x squared minus 15x plus 12. I'm positive to negative. So right there is 1. That's a sign change. Changing from negative to positive, there's another one. From positive to negative, that's another one. And then from negative to positive, that's another sign change. So there are 4 sign changes in the original function. So that means the number of positive roots must be that number we just got, or, and I just keep subtracting 2 until I can't do that anymore. 2 or 0. Has to be one of these 3 things. Okay, now I replace all my x's with negative x's. All the way through. Replace all the x's with negative x's. Even powers will kill the negative. Odd powers will keep the negative. So f of negative x to the 4th, it's an even power. Don't care about the coefficients. Even power, going to kill that negative. Here, I'm going to keep the negative. So a negative cubed is still negative times this negative I already have. I'm going to have plus there. Negatives to the 2nd power kills the negative. Here, a negative times a negative is a positive. Now I go through and I count my sign changes. Positive, positive, positive all the way through. 0 sign changes. So there are 0 negative roots. So say I started with this guy and I was doing rational root theorem on it. And I listed out all the possible rational roots. Just using Descartes' rule of signs here, I know I don't even have to bother trying any of the negative roots. None of them are going to work. It's impossible. None of the negative roots will work. So I know I only have to try the positive ones. Okay, let's make up another example here. So say we have g of x equals x cubed minus 4x squared minus 3x plus 5. Okay, so sign changes. So this is for positive roots. We use the original. I've got one sign change. Stayed the same, changed again. Another sign change. So two sign changes. So the number of positive roots must be 2 or 0. I keep subtracting 2 until I can't subtract anymore. All right, now we replace all the x's with a negative x in parentheses. So we get negative x cubed minus 4x squared plus 3x plus 5. Negative, negative, because this negative gets killed by the square, but that negative there comes along for the ride. Negative times the negative is positive, and so how many sign changes do we have? I start negative, stayed negative. That's not a change. Here I change from negative to positive. There's one. Stayed positive. There's only one. Only one sign change when I replaced all the x's with negative x. So that means I must have one negative root. So if, let's just pretend here, say I had gotten 9 sign changes, then the number I might have would be 9 or 7 or 5 or 3 or 1. However many sign changes you have, you start with that number and you keep subtracting 2 until you can't subtract 2 anymore without going negative. That's not what we had here, though. We only had one sign change. So that means I can't subtract 2 from that. You can't have negative 1 roots. We can't go negative here. That means we're guaranteed there must be one negative root. Negative real root. So this guy is guaranteed to have an x-intercept. It's guaranteed to have a real solution. See here, I might have 0 positive roots. So when I got to here, I don't even know if this thing has any real solutions at all. It might have 2 positive roots, which would then guarantee that it had 1 negative root, because you can't have one complex solution. Complex solutions always come in pairs. So when I got here, the possibilities were I got 2 positive roots and 1 negative, or maybe no positive roots, possibly 1 negative root and 2 complex roots. And that lines up with this possibility. So we might have, here are our possibilities. 2 complex, which would come as complex conjugate, and 1 negative, or, so that's that this corresponds to 0 positive solutions, or 2 positive and 1 negative. Those are the only possibilities. Okay, good place to stop.